Welcome back. So, in previous lecture we discussed mostly about the difference between the primary structure and the secondary structure, and what sort of shear fabric we should look in the trenches and all that. So, let us move ahead. In one of the slide I told that the colluvial deposit which is been seen due to the erosion of the fault scarp at the base of the fault scarp that can be used to identify the events. Let us see the importance of the colluvial wedge in this lecture. So, colluvial wedge model helps in identifying the events in many of the trenches which we excavate, and this also again remains common for all other environments, whether you are opening the trench in the strike slip environment or the normal faulting environment, or you are having the reverse or thrust faulting. So, colluvial wedge deposit, it is an conceptual model again and utilized for deciphering faulting history. So, this is important for us that we can use the number of colluvial wedges which are seen, and how we will differentiate between the colluvial wedge and the other deposits. I will come to the slides in few minutes. Okay. So, mainly we utilize this to decipher the faulting history, that means how many earthquakes have occurred along that particular fault, and this can be done by identifying the colluvial material deposited at the base of the scarp. So, just I will put a sketch here, and that can help you in understanding. So, suppose we have faulting which has occurred in case of the, either you take the normal fault where this block has moved down, sorry, and in case of the reverse fault you will have this block is moving up. Okay. So, now over the time there will be an erosion which was been shown to you in the previous lecture, that you will have the erosion here and then deposition over here. Okay. So, what you will see is that if I just modify this part here, then you have this scarp profile which is going like that. Okay. So, and the previous one was sitting somewhere along this line here. Now, you have the final this profile, and that also depends on the angle of repose, as we have discussed in the previous lecture, that when the slope is at around 30 degrees or so, then this will become stabilized. Okay, no more erosion will be there. Of course, a slight will take place, but not as much as what has been eroded initially from this scarp. And this portion will have your material which we will term as an colluvial material. So, whenever there is next earthquake, this colluvial deposit will also get displaced. So, if you are able to pick up the colluvial material, and that as I told that I will be coming in the next slide, that how you will differentiate between the colluvial material and the rest of the material in that area which has been faulted, you will be able to talk about the faulting history. Similarly, here you will have like the erosion of this scarp, and then you will have another surface which is coming up. So, you will have the deposition taking place at this base. Okay. So, finally, what you see is that you have the fault is sitting somewhere here, or maybe not exactly cutting the colluvial material, but the fault will be covered by the colluvial material, and you will have the profile something like that, and previous one was like this. Okay. So, considering the colluvial wedges, one can talk about or get back into the history of faulting on that particular fault. So, this was the slide which I have shown previously also, that you have a scarp which was formed in 1954 earthquake in Nevada with a magnitude of 7.2, and the scarp height was around 3.3 meters, and what we see is a small amount of colluvial shed, okay, the material which was eroded and deposited in this region. Okay. So over the time this will also get covered up, and you will have the preserved material, that is colluvial material, along with the scarp profile. Okay. So this will be your colluvial deposits. Now when you open up the section, because this is the exposed fault scarp, but when you open up the section, how you will differentiate this with this one. Okay. So one thing which I would like to mention here is that the material which has fallen on at the toe of the scarp is very loose. It is not as it will not show this the structures which you will be able to find out from the scarp material or the displaced material or intact material. It will show some sort of an difference in terms of the material, in terms of the compactness as well as the orientation, if you are having larger blocks which have been eroded and deposited over here. So let's see quickly that what we will be able to make out with the help of the colluvial wedges. Now here in this trench you have the colluvial wedge 1 and colluvial wedge 2. So this is in case of the normal faulting. So having two colluvial wedges, you can easily differentiate between the normal deposits which have been seen here. So this colluvial wedge has been kept by the next depositional event, but you can easily differentiate between the, and colluvial wedge will not going to extend for far distance from the scarp, as we can see here. Okay. So they will not be deposited. So we will have the coarser deposits here and finer one somewhere sitting a little far away, and that what we call the wash slope deposits. So based on this, we have C1 and C2, two colluvial deposits are there. At least you can infer that this fault has experienced minimum 2 earthquakes based on the exposed section you have in this trench. So if you recall this process, so you are having initial surface here faulted, and the other processes which are operating along the free face will be your debris debris slope deposit and wash deposit. So in this portion you will see more of coarser deposits, and then if you move slightly away from the scarp, you will see the finer wash slope deposits. Okay. So faces model, if we take in comparing the debris faces, they will be poorly sorted, poorly stratified, coarse grained material, larger class of intact soil horizon from upthrown side. So what from the scarp you will have the intact soil horizon. So you can have the larger class or larger blocks which are coming and getting deposited in form of the debris deposit. So as you refer that in the previous slide, we have the debris faces or the debris slope sitting very close to the scarp. Then it will have little matrix, continue to deposit until the free face disappears. So this is the point which we should refer to the slope stabilization. So this process of deposition of the debris with the coarser material will continue until slope is getting stabilized. Okay. And the wash faces will be comparatively finer, well sorted, okay, well stratified, fine grained, matrix supported and rich in organic matter. Okay. Deposition starts after disappearance of the free face. So if you refer the previous slide, so what we had was that you had like the surface here, and then you are having the surface over here which was been shown, and then in this slope what we see is that you have So, here you will have all debris, okay, and this will stop the debris will stop, deposition of the debris stop until the slope disappears, that is, in free face disappears and slope is stabilized, but the finer one will wash face, which will be somewhere here. Okay. So, you will see that, and they are comparatively finer and well sorted. Okay. So, mainly the slope deposits will be the part of the slope wash process, okay, and they will be during the rain splash or creeping, because of the creeping. So, these are the main difference between, you can identify as a part of the debris, or sorry, as a part of your colluvial material, where you can differentiate between the debris faces and washed faces. Now, taking into consideration the colluvial wedge material, how we will be able to identify the different events, and what other parameters should be taken into consideration has been shown in this sketch. So, for example, if you are having the faulted surface, so you are marking this as a surface which was displaced along this fault. Okay. So, the displacement was around 2 meters here. So, over the time, what you will see is the erosion of this surface here. So, if you extend compare this one with this one here, then you had like this fault is extending here. Now, this got eroded and there will be a deposition here. Okay. So, this scarp in total, what you see at the end, like what you are having at the E, then you are having at least 2 earthquakes have been identified. Now, how? Let us see quickly. Okay. So, the first event, 2 meter displacement. So, you had then 2 meter displacement, where this surface and this surface was the same pre-faulting surface was been displaced along this fault. Okay. So, this is your fault plane. So, erosion of scarp, this is now we are talking about the B here. So, erosion of scarp and deposition of the colluvial material. So, you see this as an colluvial material. So, an aggradation of 1.5 meter of post faulting alluvium buries the lower 3/4 of the fault scarp. So, what we see is that we have after this we see this one here. Okay. So, you have the deposition of the alluvial material, which covers almost 3/4 of the scarp. Okay. So, you have deposition of 1.2 meter, and one thing which you can keep in mind, that you will have the depositional structures sitting in this. Okay. So, you have a very clear depositional structure. So, if you take B, then we have the that for A, of course, there is a displacement here, and then getting into the B, this part, 2 parts will be covered here, and then further the second event. So, after this deposition, now what we in section, because it is we have we are also looking in the section, but in real case on the surface you will not be able to see this part. Okay. So, what you will be able to see on ground will be this profile. Okay. So, what you see here is that you have the scarp which is showing the height. Okay, because you will take this as an height here. Okay, with respect to this one. So, that is only half a meter which is left out, and rest was been covered by the depositional event which is of height of like 1.5 meters. So, on surface only this profile is available. So, what it says the third one, that is your C, second event again was of 2 meters. Now, this again depends, this is a very hypothetical case, but you may not come across the same amount of displacement during first event and the second event. Okay. You may have different displacement, okay. But let us take the same displacement which are occurring in in event 1 and event 2. So, second event there is a displacement of 2 meters again. So, what we have 1.5 was already left out on the surface, and then we have 2 meter here. Okay. So, erosion of scarp and deposition of the second colluvial material. So, this was the surface at the time of the second event. Okay. Or second earthquake. This was the surface. Now, with respect to this surface, what we see with the older one here, so we have the scarp height which goes up to 2.5 meter. But 5 meter was available, that is here because of the deposition here, which has gone for 1.5 meter, but the actual was 2 meter here. So, what has been left out for 0.5 meter is also been added as an cumulative scarp height here. So, we have erosion of scarp and deposition of the second colluvial wedge here at this place. Okay. So, E, what we see is the total scarp height is getting what I was explaining here is now 2.5 meter. So, this 2.5 meter scarp height, okay, is the total scarp height is not equal to either the single event or the double displacement. Now, this you will not be able to figure out unless and until you are not having the complete section exposed. Okay. So, after this event, that is earthquake event 2, what you have after the erosion and all that, you have the profile which you will have something like this. Okay. So, this height you take, then it will be 2.5 meter. Now, the actual displacement is not exactly the same, because what we have started with that 2 meter displacement in one event, and then another event was also with the 2 meter displacement. So, what we are undersizing the amount of displacement here. Okay. Now, in this case, the vertical accretion has occurred, and to justify 2 event, the best clues are what we have is 1, the down thrown block surface is horizontal, whereas the up thrown surface is dipping at slightly sloping surface, like with the 5 degree of that. Okay. And this, if you remember, if you read out this, the slope of the surface was around 5 degrees. Okay. So, this was the original slope, and that original slope you will be able to see from this one. Okay. So, this and this one. Okay. So, I will just put it in slightly bolder lines, so you can compare this two. So, these two are having your slope of 5 degrees, whereas the slope of the surface which was formed later on, that is this surface. Okay. So, you are talking about this one here, okay. This surface or this surface and this exists here, okay, is horizontal. So, when we looked at the change in the slope of these two surfaces and compared with the block here, then it can be easily we can make out that this is not the actual surface which resembles or is matching with this one. Okay, because this is almost horizontal. So, this is one clue which we can take into consideration. Okay. And then second is the soil profile on the down thrown block, that is what we are looking at here, does not match the soil profile on the up thrown block with vertical lines. Okay. So, if we consider that, okay, fine, this was the slope or this was the surface which was available at the time of the earthquake, and when we match this the soil of this one, okay, and the soil or the material with this surface, then it doesn't matches. Okay. So, that what we are trying to explain. Okay. So, we have like this has a difference, and this matches with the surface or the material which is sitting further down at around 4 meters. So, having understanding of the soil or the sediment type is also important when you are going to infer about the amount of displacement. So, this surface and the material as well as the slope matches with one another. Okay. So, these two were the same. So, total displacement what we are having here is of 4 meter. Okay. Now, if we measure between this two, then we have 4 meter, but when we measure between this surface and this one is 2.5 meter or so. Okay. So, this can take this type of exercise helps us in identifying that probably they were not a single event, but this total scarp which we see here of 4 meter is because of the cumulative event. And if you come across the colluvial wedges here, so colluvial 1 and colluvial 2, so this is older one and this is younger one, that also helps in justifying that this 4 meter is the result of two events and not the single event. And again, with the help of this, you can take 1.5 meter here, which was been covered, and that you can understand that how much was the total actual displacement during this event. So, these are the techniques or the exercise one has to carefully do when you are opening up the trench. Okay. So, what all expertise we have or understanding we have applied here, that we have taken into consideration the slope of the different contacts here and compared with the surface which is exposed on the scarp on the upper part or the upthrown block, and the downthrown block here which is covered by the alluvium, and also we have compared the colluvial wedges here. Now, compound fault scarp formed during the Bora Peak earthquake, and that can be seen here what we were trying to explain in the previous slide. So, this is an actual ground photograph. So, you can easily make out that there is slope here is gentler, okay, and then as you come here is much sharper here, and then so the slope between this, of course, the photograph is not so perfect here, but of course, the slope is wider here, and then you have the very sharp young displacement which has been seen here. So, this is young displacement, this is older one. So, over the time this will be like something like you will find that this is having like this structure. Okay. So, in that case what you will have is that you will say that okay, fine, the total displacement between the ground and the upthrown block is say for 4 meters here, but this 4 meter is not during the single event. This is showing the cumulative effect. So, we usually also usually take into consideration the angle of the surface here, as well as we will take into consideration the slope of the surface, the existing surface on the upthrown block and existing surface on the downthrown block, as well as the slope which we find while taking the precise topographic mapping. Okay. So, even with this profile we can make out that there is a break here at two locations, which can also tells us that this scarp is a cumulative or compound faulting scarp. Okay. So, another example, so that we have like what you will see at the time of the young displacement or the recent displacement, very sharp scarp, okay, and over the time it will get modified because of the erosion. So, this scarp is from 4th April 2010 earthquake in Sierra al Morro. This is in Mexico US border, and another this is your DIM which shows the LIDAR data which shows the scarp, okay, very sharp here. So, right now what we see is very straight sharp line, but over the time this will be modified something like that. Okay. So, relation between the geomorphic surfaces and fault scarp. So, the previous part which we were talking about was related to your the stratigraphic record. Okay. So, we need to complement both the data actually, what we see on surface and what we will be able to see in the stratigraphic section. Okay. So, the previous part which I have discussed will remain same for all environments, okay, because the scarps will be formed in all environments and the erosion will not be having any boundaries that if it is taking place in different environment, it will be more or less similar. So, relation between the geomorphic surfaces and fault scarp, this part is also important and this remains applicable for other environments also. Now, what has been shown here is very important and useful when we are looking at the displaced surfaces or displaced landforms along the fault scarp, and how we will be able to justify that how many events have been have occurred along a particular fault. Okay. So, we have like this is an example of a strike slip fault here, which shows the amount of displacement between the different surfaces. So, you have the fluvial surfaces over here and fault is cutting through this one here. Okay. So, and the displacement between the surfaces varies from along the faults. Okay. It is not the same. Okay. So, that can also help in identifying that what was the recent displacement during single event and what we see is the maximum displacement in the older surface, because if you have to list down these terraces which have been marked here like T1, T2 and T3, T4, T5 and T6. So, these are all surfaces which are showing the different amount of displacement. So, they have basically they show the that the older as well as younger surfaces were displaced along this fault, and the older one will show as a sort of an cumulative displacement what we see in the younger one. Okay. So, you will have this also has been taken up by the older. So, you have like if you look at the hill slope, so you have the mountains here which shows the displacement of 81 meters, and then T1 has been displaced by 452, 33, 10 and 6 here. So, this exercise again we did in case of the Kangra Valley fault, and I am going to discuss this in detail when we are talking about the strike slip environment, but this is what you see, and blue and red tone on the image is the anaglyph, and I will request our TAs to put an email to you people where you will be requested to at least purchase glasses, and they are very cheaper, and those glasses you can use to view the slides or the supplementary data which we will supply and to see the terrain in 3 dimension. Okay. So, this is an anaglyph of the portion from Kangra region which shows the edges here, and that what we call the terrace rises. Okay. So, when the displaced and matches the edges of the terraces, then one can easily make out that if we just match this one, there is a left out displacement between these two. So, if you match the edge of the scarp here, this matches well, but this one is not matched. Okay. So, it shows further the displacement remains. Okay. So, this clearly suggests that, and even this one is not completely matched, you have the displacement left out. This matches to some extent. So, at least we can say that the latest displacement was this much. Okay. And still it has been remaining in the older sections. Okay. So, these are again the terrace boundaries which we have marked. So, that what we will look at if and termed as in terrace rises. Okay. So, you have the these are all been termed as what you have the terrace rises. So, you have the fault here. So, you have the lower terrace and then you have the upper terrace. So, this will get displaced. Okay. So, a block diagram depicting the geometry elements of faulted terrace risers. Okay. So, these are been termed as terrace risers here, and this is the base of the riser and this is the top of the crust of the riser. And then if you get a chance to see this exposed stratigraphy, and that will mark your fault plane. Okay. Now, if you consider different scenarios, okay, of the erosion and depositional phases, because this process will keep operating after the faulting, during the faulting, and before also it must have been existing. So, suppose for example, what we see is that we have the material which has been deposited along the downslope, and this is the surface what we see BF. Okay. So, stage 1 deposition of the BF unit, and stage 2 erosion and incision, erosion, or you can say incision and partial deposition of PF units. Then what you see is that you have the this is erosional scarp, and that is not related to the tectonic, but this is the erosional scarp which is left out after the deposition of this PF unit. So, you have the channel erosion. So, river has eroded this portion whole and then also deposited PF. Okay. So, what you see is the left out this scarp. Now, suppose there is an event here, because usually what we have been taking into consideration that we have the displacement, if you see, or the two surfaces are separated by with some elevation, we may say that there is a fault here in this region, or the fault if it is crosses here. Okay. Now, one has to be very careful to differentiate between the depositional and erosional, or erosional, mainly the erosional scarps or escarpments which are non-tectonic in nature. Then if suppose you have a fault here, so what will happen if you allow this to get displaced during an earthquake, then you will see that this block has, for example, has gone up. Okay. Then what you see is the stage 3 faulting results in displacement of both the surfaces, that is your BF and PF. Okay. Both the surfaces are been displaced here. Now, in this case, in spite of single event, two fault scarps are formed. Now, these two fault scarps, because you have the fault trace here, okay, and this is in section you have the fault, and the fault trace is running like that. Okay. So, you have one scarp here, another scarp here. So, you may confuse that you have the two faulting events, okay, or two earthquakes here, because you have two fault scarp, but the amount of displacement is same. So, based on that, you can at least be able to justify that both the scarps were formed during single event. And not because of the two events. Okay. Now, so this is the case when you are having erosion is greater than deposition. So, erosion is greater than deposition. The erosion, the deposition was not able to cope up the erosion which took place. Okay. So, it left out the portion here, and that is one of the reason why we see the scarp here. So, this is an erosional scarp here which is left out, which you can compare with this one, and this is your this two scarp along the fault is the tectonic scarps. Okay. So, this is because of the single event. Okay. Now, we see multiple event, the conditions remains the same, where erosion is greater than deposition. So, again we will have the deposition of BF, okay, and then we have the erosion is greater than deposition, then you have the displacement, and this is left out, this part. Okay. And it's the stage 3, the erosion of the faulted surface. So, you have the because we are talking about the multiple events. So, event 1 has displaced the BF, has resulted into the formation of scarp. Now, the erosion of the faulted surface and partially deposition of PF unit, okay, leaving behind a cliffy bank. So, what we see here is that you have this part which existed because of the displacement here, okay, and this portion, whole portion was been eroded, okay, which we can see here, and then partially covered because of the deposition here, leaving behind this cliffy bank here, okay. So, stage 3 and further if you go to 4, what we have the second event. So, again we are displacing. So, what will happen, this will also get displaced, okay, along this line. So, this will also get displaced as well as this one, okay. Now, the height of this or the scarp height of this displacement will not match this one, okay. So, then in the second one what we see is that it displaces both the surfaces PF and BF, okay. Though the amount of slip was same, that is during 2 events the amount of slip, say in first event it was 2 meters, in second event it was again 2 meters, okay, but the BF surface shows the higher scarp, okay, and a higher scarp as compared to the scarp which was dislocating the PF surface, okay. So, BF surface is showing higher scarp and the PF surface is comparatively lesser one. So, because this was during the recent event, but leaving behind the cliffy bank in the down thrown block, okay. So, you have the cliffy bank here, okay, and you have the displacement which has been taken place here, okay. So, you have much more higher height. So, you can easily make out that this is not related to the single event, but there were two events, okay, here. Now, let us take the example of where the erosion is equal to the deposition, okay. Now, in this case again we will deposit BF surface or the BS material unit, and then we will have the erosion. So, erosion is leveled by the deposition, because we are taking the scenario where erosion is equal to the deposition, okay. So, the erosion and will be in the second stage complete channel fill deposits, since E is equal to D, that is erosion is equal to deposition. Then stage 3, what we see is the faulting results in displacement of both the surfaces, okay, BF and PF, and result into formation of a single fault scarp. Now, where the erosion was greater than deposition, then we had 2 fault scarp of same height, but here since these are 2 leveled one, okay, so then we see that we have this one full surface, but of course the age of these 2 surfaces are different, whereas these 2 surfaces are also what we see here, okay, and it has resulted into the single scarp. So, we need to be very careful when we need to date the surfaces, which can help us in comparing that what are the ages and of this fault scarp, okay. So, this is the event single event. So, this is the case in the single event, and when we are having erosion is equal to deposition, same, both are equal. So, again if we look at the multiple events and we keep the process similar, like erosion is equal to deposition, then again we deposit unit BF, and then the erosion is equal to deposition, and but before that we had one faulting here, and that will be, so whatever the erosion has occurred is been covered, but this part is because of the faulting, okay. This is nothing to do with that, because this was the portion which was eroded and filled up by the next phase of aggradation or deposition, which deposited PF, okay. So, this faulting event has been kept by PF unit. So, we have erosion of the faulted surface and complete channel fill deposition, since E is equal to D here. Now the fourth stage, in case of the second event, it gives you a different scarp height. The fault runs here, but what we see is that you have the different for scarp height. So the second event displaces both the surfaces B and F, though the amount of slip is same. BF surface shows higher fault scarp as compared to the scarp in PF. Okay. No cliffy bank has been seen in the down thrown side. So this can help you in justifying, because no cliffy bank has been seen on this one, but you are able to see the two scarps in this one. If you quickly look at what we saw in the previous one, okay, so we had like only one scarp, okay, so but here we see two scarp, and these are the indicative of your multiple one, okay. And in the process what we had, the erosion is equal to deposition, okay. So this can help to some extent that and justify that this was the event which resulted into the cumulative displacement, which you can see here, and this was the latest event. So with this I'll end this lecture here, and we'll see more in terms of the other environments in the next lecture. Thank you so much.